So in the previous video lecture, we have seen about convolutional encoder and its code tree representation. So we have seen that in case of convolutional encoder, we take an example with n is equal to 3 and L is equal to 2, with L is the number of modulo 2 adders and N is the number of shift registers, or we also call it as constraint length. The convolutional encoder is a form something like this. We have 3 shift registers and 2 modulo 2 adders. And the 2 output terminals are VK, 1 and VK, 2, and we give input data stream from here. So this acts as your convolutional encoder, and depending on the input data stream and the previous data available in the shift registers, we get the code word. Okay. And we have also seen the code tree representation of the same encoder in the previous lecture. Now in this lecture, we are going to analyze the state transition diagram representation of the same convolutional encoder. That is, we are going to analyze the state transition diagram representation, which will give you a better insight of this overall encoding process taking place. So the encoder behavior can be also seen from the perspective of finite state machine. We are going to analyze the behavior of encoder from the perspective of finite state machine. With the help of the state transition diagram. So whenever a data bit enters the shift register, we have seen in this convolutional encoder, whenever the data bit enters the shift registers, the output bits are determined. These output bits are determined not only on the basis of this input data bit, but also on the data bits present, previous data bits already present in these 2 shift registers, right? So there are 4 possible combinations of 2 previous bits. Okay, so let us make these 3 shift registers again. So the input data is given from this side, that is, it is given to the shift register DK. This is the input data, and the output data we have seen from the encoder. The output data depends on the input data as well as the previous inputs present in the shift registers in DK plus DK plus 2, right? So there are 4 possible combinations of DK plus 1 and DK plus 2. There can be 4 possible combinations present already, right? It can be 0, 0, it can be 0, 1, 1, 0, or 1, 1. Let us name these states as A, B, C, and D. So these are the states of the shift registers. These are the 4 possible states. So these are the states of the shift registers. So we can see that there are 4 possible states of depending on the 2 inputs which are already present in the shift registers, which can be A, B, C, D. These are the 4 possible states of the shift register, or we can say the possible states of the encoder. In general, we can say that the number of states is equal to 2 raised to power n minus 1, where n capital N is the number of shift registers. So here the number of shift register n is equal to 3. So the number of states is 2 raised to power 2, that is 4. Now, depending on the input data and these 4 states, we can easily predict the output of the encoder. This is the encoder diagram. So depending on the input bit and the 2 previously entered inputs, we can find out the output. Right? So let's say DK is equal to 0 is the input bit. Okay, it can be 0 or it can be 1, right? So it will generate four different types of output, four different sets of output depending on the state of the encoder. If A is the current state of the encoder and we give 0 as the input, we get a different output. Similarly, if B is the current state and we give 0 as the input, we get a different output. So now depending on the input data and the state of the encoder, we can generate four different sets of the output using this encoder diagram. You just have to perform this modulo 2 additions to get the outputs, right? So let us note down the outputs. Let's say for the 0 bit, if dk is equal to 0, the encoder output will be 0, 0, 1, 0, 1, 1 and 0, 1 depending on the state, if the state is A, B, C or D. Okay. So when dk is 0, the output will be 0, 0 when the state is A, output will be 1, 0 when the state is B, output will be 1, 1 when the state is C, and similarly 0, 1 when the state is D. And this table is generated using this convolutional encoder diagram. Similarly, for the case when dk is equal to 1, we can find out the output depending on the state. State can be A, B, C, D, and the outputs will be 1, 1, 0, 1, 0, 0, 1, 0. You may please verify these four outputs using the given convolutional encoder diagram. So this complete encoder behavior, that is this output and depending on the input state and the input bit, can be concisely expressed in the form of the state transition diagram. Let us see how. You can say that this entire encoding process can be concisely expressed as state transition diagram. Let us try to make the state transition diagram based on it now. So we have four different states A, B, C, D. Let us mark the four different states. Let's say this is A, which is state 0, 0. This is A. This is state B, which is 0, 1. This is state D, which is 1, 1. And this is state C, which is 1, 0. So we have made the four states depending on the previously input values. A is 0, 0, B is 0, 1, 1, 0, 1. Okay. These are the four states. Let us initially assume that we are starting with state A, that is dk plus 1 and dk plus 2, both are equal to 0, 0. Okay. Now when the input data is 0, initially we assume that we are at state A. Now we say that the input data is 0, and we are at state A, that is output will be 0, 0. Okay. So whenever the input data is 0, the output will also be 0. And state remains unchanged. This is the input data and this is the output. This is input, this is output. The state will remain unchanged. It will still be in state A. Okay, because output is 0, 0. So the bits in dk plus 1 and dk plus 2 will still be 0, 0. Okay. Initially we know that these two states are 0 because we are in state A. Okay, and we are giving input as 0. So whenever the next stage comes, this 0 will move to this shift register and this will move to this. So the new will be 0, 0. And here we'll have a new bit. Okay, so still we are in state A. Right? So when the input is 0, output is 0, we are still in the state A. Now when input data is 1, you can see, check the table, when the input data is 1, output is 1, 1 when we are in state A. Okay. So when the input is 1 and we'll move on to state B. The input is 1, output will be 1. This is the standard way of representation. Input is 1, output will be 1, and we move to state B. Why do we move to state B? Because let's say initially it was 0, 0, that is we were in state A, and we give input as 1. Okay, now when the next state comes, this 1 will move to this shift register, and this 0 will move to this shift register, and here we'll have a new bit. Okay, so now here we have a new bit, and this is 0, 0, 1, which is nothing but state B, state 0, 1. Okay, so when the input data is 1, this state transition diagram or the state transition takes place from state A to state B, and this is the input-output relationship. So this is the case when the input data is 1 and we are at state A, so it transitions from A to B. Okay. Now we are at state B, and we get 1 as input data. You can see that the output will be 0, 1. And check from here, stable. When the input data is 1 and we are at state B, the output is 0. Output is 0, 1, and we move to state D. Okay, please verify this. And similarly, when we get 0 as the input data and when we are at state B, we move on to state C, and the output will be 1, 0. Okay. Similarly, when we are at state D and the input is 1, will be at the same state, and the output will be 1, 0. When the input is 0, it transitions to state C, the output is 0, 1. From C, again, if the input is 0, it transitions to state A, and when the input is 1, it transitions to state B, and the output is 0. This way you can make the state transition diagram, which is nothing but a very concise representation of the entire encoding process. I hope you are able to understand how to make this state transition diagram. So we can carefully observe from this state transition diagram that the encoder can go to only 2 states directly by inputting a single data, whether the input is 0 or 1. That this encoder can only transition to 2 different states. For example, if we are at state A, it can either transit to state B or it can transit to the same state A by inputting any data 0 or 1. Similarly, if we are at B, it can either transit to D or C, depending on the input 1 or 0. It can go to either state B or state C. So, depending on the input data, this encoder can transit to 2 different states. So, this is really extremely important observation which we used before. The encoder goes from state A to state B. We can see when the input is 1, and it goes to state A only when the input is 0. Now, once we are clear with this state transition diagram, we have another important form of representation, which is the RELS diagram. Another important form of representation is RELS. Process. So this is another reason we are representing the code in the form of the RELS diagram. We'll start the diagram from the scratch. Okay, when all the shift registers have 0 as the current state. Okay. Let's write the RELS diagram first. So we have 4 possible states. That's 0, 0, which is state A, and then we have 0, 1, which is state B, 1, 0, which is state C. initially we assume that the encoder is in state. All the shift registers are 0 the start of the disconnect. So as we have seen in the state transition diagram, the transition takes place as we get input bit sequences. Okay. Initially we assume that we are at state and we say that the input is 0. So the input is 0, we know that from the state diagram, input is 0 and we are at state A. It will remain in state A, the output will be 0. So in state A, state A, and when the input is 1, we know that we are at state A and the input is 1. It transitions to state B and the output is 1, 1. So from here the transition will take place to state B, where the input is 1, the output is 1, 1. Okay. Similarly, this will move on to be still if we are at state A, like this 0, state A. Okay. But now here we are at state B. And from here if the input is 0, so we can check the state transition diagram. We are at state B and the input is 0, output will be 1, 0 and we transition to states. Okay. If the input is 1, we transition to state B and the output is 0, 1. So to further complete this trellis diagram for the state B, the input is 0, we transition to state C. State C. The output is 1, 0 and if the input is 1, transition to state D. Similarly, when we are at state C, we can further do the transitions. If we have the 1 as the input, transition back to state B, the output is 0, 0. And if 0 is the output, we transition back to state A. The output is 1, 1. Similarly, we complete the entire trellis diagram, which will give you another important aspect of how to represent the complete coding process. One way is using this state transition diagram, science diagrams, and using the state transition diagram, we can further make the trellis diagram. Please note that this structure of this trellis diagram is completely repetitive. It is quite expensive and can be readily known the state transition diagram that is. It should also look at the convolutional encoder. It also has the feedback and the feedback of the takes us with recursive. So that there are feedback transfer. So if the convolutional encoder has the branches, then we can make it RSC type, that is a recursive systematic RS4 cross manifold diagram. With this direct details as one of the output. This is because we are in a systematic type of diagram. Initial bits of the code are nothing but the data message. So such kind of encoder, when we have feedback branches and one of the data encoded is given that we have output terminal, must be recursive systematic convolution code These are the different types of the encoders which are used for the convolution type of encoder. Now, the next lecture is the very study the encoders for all the different types of story. Start the decoders.